Let's recall the general linear system can be written into this form. Derivative of x equals a matrix times vector x plus b, the vector b. So you see, if a system of equations can be written into this form, it is a linear system. This is the characteristics of a linear system. When this vector b is 0, then the system will become a homogeneous system. So we can write it as derivative of x equals the matrix A that can depend on T times x. So here we see a general case, right? A linear system, a general case. And when b, the vector b is 0, then we have a homogeneous problem. So for the homogeneous problem, if we can solve and find fundamental solutions of the homogeneous problem, it can help us find general solution to the non-homogeneous problem. So look at the two. This is a simplified case because b is 0. But if we solve this homogeneous problem, and then later we can understand solution of non-homogeneous. So that's why we want to tackle the homogeneous system first. There's a very important concept, which is called the fundamental solution. So let's define the fundamental matrix. So what is the fundamental matrix? It is a matrix. Yeah, so the fundamental matrix for the system. Yeah, so a general linear system, right? What is the fundamental matrix? Fundamental matrix for this general linear system, it is a matrix G, which has n columns. So this, let's say gamma 1 is the first column of G, gamma 2, second column, and the gamma n, last column of the matrix. And what is each column? Each column is a solution to a homogeneous problem. So where gamma j, which is the jth column of the fundamental matrix, it is mapping from a time interval to Rn. Yeah, so a vector, right? So this gamma j is the solution of an initial value problem. Is the solution of this initial value problem. More specifically, let me write the problem so we can So the problem is a homogeneous. It is for the linear equation, its corresponding homogeneous case, subjected to an initial condition. So when t is 0, the solution is given, which is a unit vector. So this epsilon j is a unit vector with the j's entry being 1. So let's look at very specific case. So gamma 1 is a solution of this initial value problem. So let's just make sense with the notation, because you might be wondering, then what is the gamma 1, right? So gamma 1, for example, gamma 1 will be solution to what problem? To this problem, the homogeneous problem, and initial data will be epsilon 1. Well, epsilon 1 is the unit vector with 1 in the first entry. So that gamma 1 is just a solution to this initial value problem. So similarly, what about gamma 2? Gamma 2 will be you see, will be solution to the initial value problem with the same governing equation, but different initial data. At 0 will be epsilon 2, which is the second unit vector in Rn. So for Rn. So everything 0 except for the second entry. So epsilon 2, you see the gamma 2 is solution to this initial value problem. So that means this epsilon j is just a unit vector. So you see, when the initial data changes to a different unit vector, then the initial value problem right, is a different problem, and you will get a solution curve corresponding to that problem. So gamma j will be solutions to these problems. Okay, so gamma j is the solution of the initial value problem corresponding to the initial data when x at 0 is epsilon j, the unit vector. So it's necessary to specify where. So epsilon 1 will be this unit vector, right? And epsilon 2 will be, okay, that, and then epsilon n will be the last entry being 1. So this epsilon 1, epsilon 2, all the way to epsilon n, they are different unit vectors. Yeah, they're the standard unit vectors in Rn. Okay, so now let's see if you have found solutions to these initial value problems. Then we put the n solutions together, gamma 1, gamma 2, through gamma n, right? We will form a matrix. So that matrix, so let's, okay, so we're going to say this G, which is the notation for the fundamental matrix. So this G has n columns. The first column will be the gamma 1. Second column will be gamma 2. The last column will be gamma n. So look, that means we already solve, right? We suppose we know how to solve each initial value problem. Then we will find solutions to each initial value problem. So we have gamma 1 corresponding to the initial data epsilon 1, gamma 2 corresponding to the initial data epsilon 2. So just to change initial data, we will get different solutions. And then with n different initial conditions, we will get n different solutions. So gamma 1 through gamma n. So these n solutions, we put them in a matrix. So they are n columns of the fundamental matrix. So this is what we are having now. G of T, it is the matrix, what we call fundamental matrix. Yeah, for the linear system. So first, what is gamma 1? Gamma 1, that is a solution vector corresponding to epsilon 1, the initial data. But it's a column, right? So we have to, okay, let's use this notation. So 1, 1, 2, 1, and 1. So that is the vector we represent the gamma 1, the first column. Second column, gamma 2. Gamma 2, it will be second column of this fundamental matrix. So second column will be okay. So let's use the same color. Gamma 1, that is we write in the entry form will be 1, 1, 2, 1, gamma n1. And of course, each entry is a function of t. So that column is the solution gamma 1. The gamma 2 corresponding to the initial data epsilon 2, right? We find this gamma 2 solution. So the gamma 2 also is a solution vector we write as 1, 2, 2, 2, and 2. And each entry of this vector is a function of t. So now we list the second solution, gamma 2, in the second column of the fundamental matrix, etc. So we can do this. Then the last column, so the second, yeah, so this that's the n, Rn. But the first entry, second entry, last entry of gamma n, right? We denote it by this gamma 1 and 2 and nn. So each entry is a function of t. So now we have each column. So you can see better this way, just gamma 1, gamma 2, each one of these gamma columns will be a solution to a certain initial value problem. So we put them here, then you get a matrix. This matrix is called a fundamental matrix for the linear system. So the linear system we're considering is with this is the general linear system. So when we define the fundamental matrix, we only restrict ourselves to solve the homogeneous problem, right? So we're looking at solution to the homogeneous case corresponding to an initial data, which is like this. So solution to this will be denoted by gamma j. So as you can see, when j is 1, which is gamma 1, we have that solution, right? When you vary the initial data, then you will get another solution to the initial value problem. You vary the initial data to when j is n, the epsilon n, then you will get another solution to this, because each time you change the initial data, the solution will be different, because that's a different problem, initial value problem. So, okay, so once we get all the solutions together into a matrix, then let's check on the properties. We want to discover what is the special about this matrix. This matrix, if you evaluate at 0, that is when t is 0, what is the value of the matrix? So when the t is 0, then each gamma, each column, when t is 0, so you just think of the gamma 1, right? The first column at 0, the second column at 0, the last column at 0. So I just try to think of each column, right? Because each column is a function of t. Just keep in mind, no matter I put parenthesis t or not. So each column is a solution of the initial value problem, of the homogeneous initial value problem. And then evaluate each column at 0, what do we get? And gamma 1 at 0, just go to the problem, see? Gamma 1 at 0 is gamma 1 at 0, right? Should satisfy epsilon 1. Yeah. So gamma 1 at 0 will be epsilon 1. Then let's look at gamma 2. Gamma 2, the solution gamma 2 at 0, because gamma 2 is the solution corresponding to epsilon 2 initial data. So at 0, it's epsilon 2 will be this one. So the gamma 1 at 0 is the first unit vector. Gamma 2 at 0 is the second unit vector. Because of the initial conditions each gamma satisfies. So that's immediately we can write this as gamma 1 at 0 will be this unit vector. Gamma 2 at 0 will be, right, the second unit vector. Gamma n at 0 will be the last unit vector. So all the way, and this 1 at the last entry. So what are we getting? This matrix when t is 0, and this is an identity matrix. You see 1 at the diagonal entries and 0 everywhere else. So G, this matrix, fundamental matrix, when t is 0, it is an identity. So at a certain time, that means all the columns are independent of each other. Yeah, because we see the for identity matrix, right? It is an independent columns. So this is very important because it implies if at a certain time the columns are independent of each other, and then these n solutions are independent solutions. Okay, so actually the gamma 1, gamma 2, gamma n, the n solutions at initial time, we choose the initial data so that they are independent. So then eventually the n solutions will be independent solutions. So this already, you see, this is one feature of this fundamental matrix. This fundamental matrix evaluated at 0 is an identity matrix. And now let's write again. This is really the because of gamma 1, gamma 2, the definition. So we can quickly write gamma 1. It is a solution of that problem. So gamma 1's derivative with respect to t is equal to A times gamma 1. And gamma 1 at initial time will be epsilon 1, right? The first unit vector. So this is what gamma 1 is because we solve the solution of an initial value problem. And what about gamma 2? Gamma 2 is solution to this homogeneous problem. So recall that gamma 2 solution to this, right? Yeah. So you put gamma 2 into this equation, it will satisfy the problem. And gamma 2 satisfies the initial data. When t is 0, the gamma 2 is the second unit vector. So that is what gamma 2 satisfies. So we just, that is how we define the fundamental matrix by finding solutions to these initial value problems. So then similarly, gamma n. So let's just write more. Gamma n the last one, gamma n satisfies the same homogeneous equation, but satisfying this initial data, the last unit vector. So when time is 0. So gamma n satisfies this. So these are the specific properties of the first column, second column, and last column of the fundamental matrix. So just to look at the gamma 1, gamma 2, gamma n again. So let's put this again into a matrix form. So if we put in the matrix form gamma 1 derivative gamma 2 derivative, gamma n derivative. Because we have n columns, we can put them into a matrix. So these are simply gamma 1 derivative. Recall that it is the AT times gamma 1. Gamma 2 derivative is AT times gamma 2. Gamma n derivative is AT times gamma n. So we just simply used the fact. You see, the fact is that gamma 1 derivative, right, can be rewritten as this column. It is the same as matrix times this vector. That's the vector. So this vector is same as that vector. We just replace it, right? Gamma 2 derivative is same as A times gamma 2 because each gamma column vector is solution of this homogeneous problem. So we just simply replace it using that identity. So that's what we're getting. So this is G. Look, this is actually the G fundamental matrix, right? That derivative, because you take a derivative of each column of G. That is a derivative of fundamental matrix. And then if we rewrite, we discover this A can be put outside and times, so this n columns, gamma n, which is the fundamental matrix. You see the G derivative, and what we discover is that this is a G. That's the fundamental matrix according to our definition. That's the fundamental matrix. So fundamental matrix derivative equals A times fundamental matrix. So now we arrive at this matrix equation, which is, I just simply rewrite, this is our G. You see, it's not surprising because if we each column, right, of the fundamental matrix satisfying this differential equation, you see second column satisfying this same equation, then the matrix itself satisfies the equation. But it is a matrix. Matrix derivative equals A times the matrix. So the same form. Because each column of this matrix satisfies the equation. So the matrix also satisfies the equation. So we can write now a clean version just to write the fundamental matrix derivative equals the matrix times G. So this is a matrix equation. The fundamental matrix also satisfies equation of with a similar form. And this matrix, when T is 0, is identity matrix. It is identity matrix. And n by n identity matrix, suppose A is n by n matrix, then this I is also an identity of the same size. So now you see the fundamental matrix and its definition. So let me give you one system so we can just make sense with the notations by looking at a fundamental matrix. So here is an example. And this example, we have this form, and this A is given as okay, let me directly write in the place of A. So you can see this A is the matrix, 2x2 matrix. And times X, right? So we can put X. But as you can see, the X is a R2 in R2. So we can simply write in the X1, X2. Okay, X1, X2. That is, so X1, X2. So vector valued functions of T. So there are entries of the X. The first and second entry of X as a vector. So this is just exactly that form, X equals A times a certain X. So you see a very concrete homogeneous problem here. So the homogeneous problem, the X is in R2, right? Derivative of X, yeah, A is a 2x2 matrix. Now, fundamental solution. So first, let's, okay, consider gamma 1. What is gamma 1, gamma 2? Right, so gamma 1, because we know the fundamental matrix is a matrix formed by gamma 1, gamma 2 for this problem. And gamma 1 will be solution to the same equation. So let's just, for the simplicity, I will just call this equation because we know this is A, right? So we know this is our A. This is our X. This is our X derivative. So that's our equation. I just write it instead of this complicated form. So you know that's A, specifically this 2x2. So gamma 1 is a solution of this homogeneous problem with that matrix A. Okay, I can put gamma 1 because gamma 1 satisfying this homogeneous problem. Yeah, this one, the homogeneous problem. So that's why gamma 1 derivative equals A times gamma 1. And gamma 1, in addition to satisfying that homogeneous equation, gamma 1 also satisfies this initial data. That is, when t is 0, gamma 1 takes the value, yeah, epsilon 1. That's the first unit vector in R2. So that's our gamma 1. Gamma 2, let's write gamma 2. So gamma 2 is also solution to the same homogeneous equation. So let's simply write gamma 2 same equation with that matrix A times gamma 2, right? Same equation, except the gamma 2 at 0 is a different initial data. So it will satisfy 0, 1, the second unit vector. So this is gamma 2. So if we can find gamma 1, gamma 2 by solving the two systems and recall that A is given, right, for this specific problem. So A is given. And we just solve this very specific initial value problem and this other initial value problem. Then we find gamma 1, gamma 2. So without going through this, but I will just write the solution, assuming we get the gamma 1 and gamma 2 as function of t gamma 1 by solving the first initial value problem. It is 1 minus t squared minus 2t. Yeah, this one is solution of the first initial value problem, and then gamma 2 solution for the second initial value problem. So let's put solution next to our problem so you can also see. I will just put next to the problem so you can see gamma 1 after we solve it. Solution to this problem is 1 minus t squared minus 2t. That's solution of the first initial value problem. Gamma 2, solution of the second initial value problem, t minus t squared, 1 minus 2t. So it's okay, but at least you can verify, right, whether this is a really solution of that problem. Just to substitute this, take a derivative of this with t, see if you get the matrix times gamma 1. Do you get the same thing, right? You can easily verify. And this gamma 1, when t is 0, you see, when t is 0, it's a unit vector, 1, 0. Yeah, satisfying the initial data. And gamma 2, if you want to verify, you can also, by substituting this gamma 2 into this equation, see if this gamma 2 satisfies. Yeah, it should satisfy if it's correct solution. And also gamma 2 satisfies the initial data. When t is 0, it is 0, 1. So when t is 0, the gamma 2 satisfies the initial condition. So now we have found gamma 1, gamma 2. Suppose I put the two vectors into a to form a G. So what is our G, fundamental matrix? Fundamental matrix G will be first column being gamma 1, second column of G being gamma 2. So here is our fundamental matrix for this linear system. So the first column is gamma 1. Second column is gamma 2. Okay, so that's the definition of a fundamental matrix. And this matrix is very useful for us to represent general solutions, because after you find, basically for this example, we find two independent solutions, because you can see when t is 0, this is a 1, 0, the other column is 0, 1, right? They are independent. So these two solutions are independent, and they can represent all solutions of the homogeneous problem. A general solution to this problem. Because without specifying initial data, if we look at this equation, we have infinite integral curves. How do we represent a general solution to this problem? We can use the two independent solutions, and the arbitrary combination of these two solutions will generate all solutions. So actually, we can use this G So to represent all other solutions, although this G has only two solutions, right? First column, second column, the two integral curves corresponding to specific initial conditions. But if we write C1 that is times the first, that's gamma 1, C2 times gamma 2, then this is an arbitrary linear combination of these two solutions. We know that for homogeneous problem, the linear problem, if both are solutions, then their arbitrary linear combination also a solution to the problem of this x prime equals a t times x. So because both gamma 1, gamma 2 are solutions of this problem, then arbitrary linear combination will still be a solution of the homogeneous problem. So this is our general solution, X. And you see the use of columns of this fundamental matrix, we can represent the general solution to the homogeneous problem. And also we can write this general solution into a matrix times C1, C2. Let's write it in matrix form. The first column is, second column is, just simply, you see the first column is the gamma 1, second column is gamma 2. So in matrix form, that's the G, right? Fundamental matrix times a C vector. So a general solution can be represented with a fundamental matrix times a vector, C. So through this example, you can see a fundamental matrix is useful in such a way that it is being used to represent all solutions of the homogeneous problem, or a general solution of this homogeneous problem.